This is my first time in Africa, and of course first time in South Africa, and what a beautiful place. I'm really happy to be here. I heard a lot about AIMS, and before I came here I told my stepmother, who's not a mathematician, I was going to come here, and she goes, I know all about AIMS. That's where the next Einstein is coming from. She'd heard about it on the Canadian news, right? There was this documentary and a lot of discussion, so very high profile. And so I'm very interested in invasive species. I've worked on them for quite a few years, and I'm really happy to be here after the series of very nice talks we had this morning. And so Yuri told us about the general problem of invasive species, and Abba told us about the way that we use R0, amongst very many other things, to understand epidemics. And what I want to talk about is something very similar, except now for invasive species. But the difference now is that we're going to look at the kinds of models that Jacek was talking about, and they were in discrete time rather than continuous time. And rather than start and give an overview of modeling of invasive species with mathematics, which is a very large area, I want to try a different approach. I want to look at a very specific example and get into some details, and then build up a more general theory from the specifics. Now, when a species is introduced, there is this little window where it's at low densities. And then it can grow and thrive and perhaps spread. And of course, we might be very interested in knowing how quickly it's going to grow when introduced at low densities, and also in seeing if we can control it at very early stages. And in that respect, there's lots of kind of analogies between invasive species and diseases. And so there's a very beautiful flower shown in the top right here. And this is an invasive species. And we heard that the British were very effective at keeping the muskrat out of Britain. But they've also been very effective at creating species or having their species spread to other continents, mainly through colonization. So people that have emigrated to other countries, such as Canada, will bring species with them that they like from their homeland. They look beautiful, and then they grow, and then sometimes there's a problem. And we call these problems weeds often, okay? And this is a weed. This is called Scentless Chamomile. It may not look like a weed, but it gets in with the wheat, the other agricultural crops, and it reduces productivity by competing with it. And so this is an annual, biennial, or short-lived perennial. And it prefers disturbed habitats where, say, a farmer's field would be a very good place for this weed to grow. And it invades agricultural ecosystems, and then it reduces the cost. Now, the cost of invasive species, all told, is very high. And I imagine Dave Richardson will talk about that more in detail when he's speaking, so I won't go into that. But they incur very significant costs in the order of hundreds of billions of dollars a year in North America alone. So if we look at this plant, it's got flowers. Okay, and these are the things that produce the seeds. It's got rosettes. These are these small non-flowering plants. And then it's got seeds in the ground, and that's the seed bank. And so when we think about an invader, we really need to think very carefully about the life history of the invader. What structures are there? And every invader is different. We can draw the life history in terms of a graph. And so here we would census, say, around May or June, okay? And there could be seeds, okay, in a seed bank in the ground. There could be these small non-flowering plants called rosettes, or there could be these flowering plants with flower heads, and these are flowers. And if we're going to think about this mathematically, we can think about transitions from one stage to another. And so a flower produces a seed, it falls on the ground. It could go into the seed bank, and that's what this arrow shows here, and not flower initially. Or that seed could grow up and form another flower, and that's what this transition describes here. Or the seed could germinate and form a rosette. Now the rosette doesn't flower, but it's vegetative, okay? Similarly, a rosette maybe next year becomes a flower, okay? Then it would have been a 2-year life cycle. The seed could stay in the ground for any period of time from year to year, and then it may become a flower or become a rosette. And so this is actually a rather simple example of a stage life cycle that we have to really understand if we're going to look at what we can do to control it or how we can understand how quickly it will grow. And just as with ABBA, please stop me and ask questions if you'd like to. I know he got a lot of questions. I know this is risky because it might mean I don't get through my talk, but if I don't get through my talk, I'll be very happy because that means you're listening to what I'm saying and have questions. Okay, so this is just an example of other plant species that are weeds in where I live, okay? And without going through, except this bullfrog is of course a frog, and without going through all the details, we can draw these life cycle graphs for each of these invasive species, and each of them is different. So there's all these diversities of different strategies and life histories that different invaders have. And somehow the devil is in the details, so these really matter if we're going to try to figure out how quickly they grow or if we can control them. Now, the graph is a beautiful way to look at these transitions. The arrows with a slightly red tint to them are to do with the production of new individuals. So when we have a flower, it produces new seeds into the seed bank. It produces seeds that turn into rosettes or then seeds that turn into flowers. And so these are fecundities. The ones with the black transitions are survival. So they're numbers that are going to lie between 0 and 1 because we're not creating any new individuals. We're just surviving maybe to the same stage or perhaps to another stage. Okay, so this is the outline of my talk. I'm going to look at classical methods to evaluate the growth of invasive species. These methods are used very widely by biologists. Okay, so they're very popular, not only to look at whether invaders will grow, but the flip side, if there's an endangered species, they would like to find a way to make sure that it does grow when it's at low levels. And so they may use exactly the same kind of model, but they're asking a very different question. And I will then talk about some quite new material which relates these methods to some of the more classical epidemiological approaches. And in this area, I think epidemiology has moved quicker than ecology. And so we can learn from our epidemiological friends and see what they do and see if we can do similar things. And then I want to come back to our example, which I'll stick with, which is this Scentless Chamomile, that beautiful weed from Canada. Okay, so this is the graph again, okay? And from a graph, you can create a matrix. And so when we label the graph, say A13, 1 is the node to which the arrow is going, and 3 is the node from which it comes. And then if we put these in a matrix with the first index describing the row and the second index describing the column, we have the index shown, the matrix shown at the top there, where there's some zeros, okay, which describe, for example, there's not an arrow from here to here. The A22 is missing, and so forth. And then if we use a matrix model, we'd say the population numbers in each of the 3 stages, seeds, rosettes, and flowers, at the next time step is this matrix A operating on the number at the previous time step. So this is a linear discrete time model. We know there are nonlinearities at play, but somehow we kind of sweep them under the rug a little bit because we know that this is at very early stages. Okay, and we're not assuming that like there's an Ali effect or anything like that, so maybe nonlinear density-dependent terms don't matter quite so much. And linear is easier to understand. So we need to know something about this matrix A. It has some properties. It's a non-negative matrix, okay? So there'll either be zeros or positive numbers in the matrix. And we'd like to evaluate the growth rate of the population. And does anyone remember how you might do that? A method by which we could understand this, if we're interested in the growth rate of the population. Eigenvalues, yeah. Eigenvalues come to the rescue. And so I'll just say a few words about these. This might be review for some people, but it's actually kind of very beautiful theory. And we'll look at it and we'll admire it, and then we'll discard it and do something else, okay? And so A is non-negative, and it has this other property which is really useful, and it's called primitivity, okay? So a matrix is primitive if that matrix raised to some power, k, is strictly positive with all of its entries. Another easier way of saying a matrix is primitive is to look at its graph. And a graph related to a matrix is primitive if you can get from every component to every other component in exactly k steps. And so if we choose k to be 2, in this case here, we can get, say, from 1 to 1 in 2 steps. We can get from 1 to 3 in 2 steps. We can get from 3 to 1 in 2 steps. We can get from 1 to 3 in 2 steps, and from 3 to 3 in 2 steps, and so forth, right? So this is primitive with k is equal to 2. And so that's what that example says, okay? It's actually easier. I hate doing matrix multiplications, so it's easier to look at the graph. But we could have squared the matrix and just checked the entries, and it would have given us the same thing. Okay, so we want to look at the eigenvectors and eigenvalues for that matrix. And so there is a kind of a classical definition. If your operator, okay, applied to an eigenvector is a constant times that eigenvector, that's an eigenpair. Lambda is the eigenvalue, and v is the eigenvector. And that's what's shown in the first definition. And so now we have the idea of an eigenvalue and an eigenvector for A. And there's this beautiful theorem called the Peron-Frobenius theorem that states that if we have a primitive matrix, which is what we have, then there's a dominant eigenvalue lambda that's real and positive and is strictly larger than all the other eigenvalues in modulus. And the corresponding eigenvector is also positive. Okay, so at the end of the day, this is going to focus our attention on the largest of the eigenvalues for this matrix A as being the one that's relevant. Okay, so if we go back to our model, nt plus 1 is A times nt, and we have some initial distribution of stages, maybe at the early stages of the introduction, early time in the introduction, and we'd like to know what happens after we apply this matrix model many times. Is the population going to grow? And so just like in an earlier example today, I think that was brought up. If we iterate t times, we just raise the matrix to the tth power times the initial data. And that's our solution. Okay, it's a linear equation, so it's fairly straightforward. And we want to know if nt is growing or not as time progresses. And so if we take our initial data, so the component of n naught that's in the direction of the dominant eigenvector will grow fastest because it's, we have a lambda, AV is equal to lambda V. And so as time progresses, things are going to look like a constant times lambda, this multiplier to some power, times the eigenvector, if we wait long enough. And so this is the key for kind of eigenvalue analysis for either invasive species or endangered species. We take our matrix, make sure it's primitive, okay, and then we interpret lambda as the asymptotic population growth rate, and V has a biological interpretation as what's called a stable stage distribution. And so what it says is after many iterations in time, and you see what you have, 1, 2, 3, if you look at that eigenvector, it'll give you proportions in each of the different stages. after a long period of time. And so this is quite useful. It not only tells you the growth rate, but the relative proportions that you should see in the population after sufficiently long. Any questions on this part? Okay, so this method has been very popular, right? I'm in a biology department and a math department, and all the biologists carry around this book by Hal Caswell on matrix models, and they open it up to the right pages, and there's a very nice explanation of what to do in terms of calculating these eigenvalues and growth rates. And mainly, they're interested in conservation biology. And so they'd like to find out if there are spotted owl species or maybe elephant species that they're studying. We have an institute in South Africa at my university. Whether they're going to grow or decay over time, depending on these transitions.
Question?
Yeah.
The fact that the largest eigenvalue is positive, is it not affecting the behavior of solution in the long term?
Absolutely, yes. The fact that the largest eigenvalue is positive is crucial here. The important issue is whether it's larger than 1 or not. Okay, so this is a really good question. If we look at this here, say in continuous time, you might be interested in the real part of the eigenvalue if it's positive or negative. The positivity of the eigenvalue comes from this Peron-Frobenius theorem. But if it's less than 1 in size, even though it's positive, the population will decrease geometrically. And if it's larger than 1 in size, it'll grow geometrically. So thanks for asking that. Okay, so this is the kind of thing that we would normally do. We look at the dominant eigenvalue of the matrix A, and it's straightforward to do this, say, in R. And if it's less than 1, the population decreases. If it's bigger than 1, the population will increase. And we're not finished, though, because we may be interested in trying to manipulate some of these coefficients. So we may want to use biocontrol or mechanical control or something like that for our weed species. And so we may say, oh, I think I know how to change Aij, one of these transitions, through some other feature. Now, in epidemiology, it might be something to do with vaccination or some kind of other quarantining or something like that. Here, it's often biocontrol or chemical control. And you might be interested in saying, which of these transitions, Aij, is the best one to focus on? And this is where this idea of sensitivity and elasticity come into effect. Now, sensitivity is simply the partial derivative of the dominant eigenvalue with respect to one of the entries. And if we think about lambda as it depends on one of the entries, it may be useful to see how quickly lambda will change if we change one of the entries. If it's highly sensitive, we could think about controlling that. More often, though, people look at elasticity. And elasticity is just a scaled measure of sensitivity. And we can think about that as the proportional change in the eigenvalue to the proportional change in the Aij. So there's a scaling here. And this is because we could measure the Aij's in different units, perhaps, and we want to be sure we're comparing apples to apples. Okay, so we've got a method we could use here for invasive species. Determine the life cycle, draw the graph, estimate parameters, get that population matrix A, calculate the population growth rate, evaluate these elasticities, and target transitions with higher elasticities. And then when we look for control agents, try to choose ones that are going to look for the Achilles heel, that one maybe transition to which a small change might cause a large downward change in the eigenvalue. Okay, let's try that here. And here we see our friend again, that innocuous looking scentless chamomile. And first of all, this is an incredibly fecund plant, okay? It produces about 250,000 seeds, which is absolutely phenomenal, right? Here's our matrix. And this is my grad student, Thomas de Camino Beck, who did this work. So we have an agricultural plot near the University of Alberta. And we're working with the Alberta Research Council, who wanted to control this weed and wanted to see if we could use biocontrol measures. And this is his field crew. That's me working hard in a little different gear than I am now. And these are the flowers in different patches. And so he managed to measure all these parameters with some very ingenious field experiments, which I won't go through. And anyhow, these are the numbers he came up. He did it for 2 years, okay? This is an incredible invader, right? It has a lambda between 20 and 300, depending on what year. This was a colder year. This was a warmer year. The weather was better, okay? But when we look at these elasticities, I think they've been multiplied by 100 because they should add up to 1. It's the flower-to-flower transitions that have the largest numbers in here. Okay, so this was the A33. It was flowers producing new flowers. And so it says we have to really find some way to reduce the fecundity of these plants if we're going to be able to effectively control them. Okay, and we can just draw these elasticities out graphically here. And the height of the bar now is the size of the effect. Okay, so I'm going to come back to this and talk about what we tried to do with biocontrol, but at the end of the talk, okay? So we'll have to keep that thought. This is what we just did, okay? This is a very powerful method, but there's limitations. And okay, what would the limitations be? Any ideas about that?
It's not primitive?
Well, for some of them it might not be, yeah, for sure. And if your matrix isn't primitive, then you need to think of something else. Exactly, yeah. Yeah, other limitations. I think I heard it twice from 2 people, like it's a linear model. Yeah.
Feedbacks.
Yeah, so there's, it's linear and there's no nonlinear feedbacks. Yeah, that's very important, yeah, yeah. What other, anything else?
About the accuracy of the measurements.
Sorry?
The accuracy of the data
Yeah,
from the field.
yeah, it's a lot of work to parameterize. Yeah, it's, it took Thomas like a couple of years to get all the parameters and reliably. Is that what you're saying, or?
I mean, will that not affect the results you get eventually?
Absolutely, yeah. So there's a great deal of variability in the data that you collect, and that will affect the outcomes. Yeah, which is sort of intrinsic problem about the biology, that these systems are not as deterministic as this might suggest. They're rather stochastic in terms of the growth every year. Yeah, anything else? Well, when I heard Abba's talk this morning, what I really liked was he could come up with a very nice formula for R naught. When we calculate these eigenvalues of these n by n matrices, you don't have a nice formula. You just have a polynomial of degree n that you put on R or Maple or Mathematica, and then it gives you a number. But you don't gain this insight. See, what I like about some of these epidemiological models is you gain this beautiful insight by looking at R naught that tells you about how each of these factors that go into the model are affecting the outcome. And so this is a key feature that unless you have a quadratic, you don't really want to write down a formula for lambda, okay? And if it's quintic or higher, you have no chance. And so, and you have to calculate things numerically, and you don't gain this new insight. So if I said, well, you know, lambda is 19.3, That's 19.3 for that particular plot on that particular year in that particular location. But I'd like to say something generally about Scentless Chamomile. So if it's an invader in South Africa, and I don't know if it is, then someone could pick up my work and then use it again without having to redo the whole calculation. Okay, so the alternative is to calculate this thing, which is very much like the basic reproduction number. But ecologists, they like to call things differently, and they call it the net reproductive rate, which is a misnomer because it's not a rate. But if you Google it, that's what it's called, okay? This is a number which is very much like the basic reproduction number would be for a continuous time model. And it describes the number of offspring a typical individual will produce over their lifetime, okay? And so we have to break down our matrix into two components. Remember early on, these things are fecundities. They're the creation of new individuals. And these darker ones are transitions. And these would be probabilities of making it from one stage to another. So we decompose our matrix A into a survival or a transition matrix and a fecundity matrix. And we call them T and F. And then this is our model at the top there. And at the next time step is A times N at this time step. But we can come up with this new operator if we want to, which is called the next generation operator. And if you're producing offspring, you might produce them this year, okay? And that would be year one. Or you might survive for a year and then produce them next year. Or you might survive for 2 years and then produce them on the third year, and so on and so forth. And so if we're looking at the number of individuals produced over the lifetime of a parent, we have this infinite series, okay? And because of the form of the transition matrix, we have a property that the rows sum to less than 1, or the columns, I think, sum to less than 1. We can write that as F, the fecundity matrix, times the inverse of I minus T. Okay, so if you had a sum 1 plus T squared plus T cubed plus T to the fourth, okay, that would be 1 over 1 minus T if we did a geometric sum. And the same is true for matrices now. It's F times I minus T to the minus 1. And that's our next generation operator. And so this puts us in a position where we can try to come up with a formula. And we describe the net reproductive rate, which is like the basic reproduction number, as the number of individuals that a single typical individual would produce over its lifetime. And it's the largest eigenvalue of this operator Q, F times I minus T to the minus 1. And it turns out that the population grows if R naught is bigger than 1 and dies out if R naught is less than 1. In fact, R naught is bigger than 1 if and only if lambda is bigger than 1. And so anything we could do with the eigenvalue, we could do with R naught, which is kind of nice. But then you might say, why make your problem harder? We just calculated lambda. Why would we go and calculate R naught? And this matrix looks a little bit more complicated than A. And so the reason, though, is there's like a little minor miracle that occurs, which always strikes me as amazing, that even though we cannot come up with a formula for lambda in general, we can almost always come up with an exact analytical formula for R naught. And to show you, let me go back to our example here. I always try to avoid doing calculations. And so anyhow, I think these are correct. And I checked them on the computer. But I'm always like looking for ways to make things simpler. So after showing you this calculation, I want to show you maybe a way that I think is a bit nicer and more beautiful to do the same calculation. But I guess you have to roll up your sleeves once, or I have to roll up my sleeves, and work these things out, okay? So we take I minus T inverse, okay? And so we just kind of do this through row reduction and so forth. And then we have our f up there. And then we have f times I minus t to the minus 1, okay? And the interesting thing is it turns out to be a singular matrix. And so every row is a multiple of or it's actually identical to the next row. And so it just has a single non-zero eigenvalue. And that eigenvalue is given by the trace of the matrix. Okay, and this is what it is here. Okay, so now for this problem, we can actually write down R naught in terms of the parameters. Questions?
I identity matrix.
Sorry?
I.
I is the identity matrix, yeah. So it's like got zeros, but it's got ones on the diagonal. Yeah, good question. Yeah. Other questions or comments? Okay, so somehow this next generation operator has two zero eigenvalues and a third eigenvalue that we can calculate explicitly, whereas the eigenvalues of A are really solutions to cubics. And so this is a lot more handy if we want to figure out the effect of each of these transitions on R naught. And we'll come back and do that in a few moments. Okay, so this is just, am I going the wrong way, maybe? Yeah, so, question, yeah.
So in your R naught, are we assuming that these transitions are always less than 1?
The values in T are less than 1. In T, but not in F. F is the fecundities, okay? So you could produce 250,000 seeds or something like that, right? Like many, many individuals in these things here, okay? But for these values here, okay, it turns out that if you add this value, A11 plus A21 plus A31, that's a number that's less than or equal to 1. Okay, in fact, it's almost always, you can assume without loss of generality, it is strictly less than 1 because there's got to be a little bit of mortality every year. Okay, so T is an interesting matrix. It's got columns that sum to, that have positive entries and sum to less than 1. And so that allows us to take I minus T and know that we can find the inverse for that. Okay. Sorry?
No, I was asking that because we have 1 minus A11 in R naught. So
oh yeah. That's a very good point there. So, yeah. So we've got this term here. Yeah. I think I'll come back to an explanation for what this is intuitively, and if I don't, remind me. And yeah, it's got a very nice intuitive explanation. And yeah.
In this case, essentially, it is sufficient that A11 is smaller than 1, just because your matrix T splits into diagonal plus nilpotent, and the series actually terminates after, I think, 2 iterations.
Yeah, that's right. So
essentially, A11 is only important here.
this is the only one that's important in this particular case. A very good point. Well, I think we do. Yeah. So the general theory needs the full series. Yeah. Okay, so as with lambda, we need to calculate an eigenvalue now of this operator, but we can write it down explicitly. At the end of the talk, I'll come back to an interpretation of the of R naught in terms of the fecundity loops. Okay, that's what it's called. But before we do that, I want to just show you if you don't, I don't like inverting matrices and those kinds of things. So I just want to show you another method to do this that is really beautiful. And you can do it on the back of an envelope. Yeah, and it doesn't even take very long. So, and it uses graph theory. So we just want to calculate this R naught for some life cycle graph. And so, okay, so basically we create the graph. We look at the graph that we started with, okay, and we do three things. Anywhere there's a fecundity weight, we multiply that by R naught to the minus 1. And then we use a set of simple graph reduction rules to reduce the graph until it goes to a single node. And then we set the weight for the final node to 1, and then we solve for R naught. And these are the rules. And these are called Mason's rules for graph reduction. And they're a little bit like the rules that you might have for electrical circuits. Like, okay, so here, if you go from 1 to 2 to 3, this would be like going from 1 to 3, and you just multiply the weights. Okay, see, there's like circuits in series. And here, if there's parallel circuits I think these are conductances for circuits. If you go from either from 1 to 2 through A or 1 to 2 through B, then you put the weight A plus B on the edge. That would be a reduction. And then the final one is if we have a self loop at an incoming node, B, then we remove that loop and replace it with the weight A times 1 minus B inverse. Okay, so these are the three rules we want to remember. And actually, my graduate student, Tomás de Camino Beck, the same person that was doing the experiments, he was a computer science student, and he came up with this method. And he was like, this is amazing. I don't know why it works. And I go, well, can you prove it? And he said, actually, I did prove it. And I said, how did you prove it? He said, I created 1,000 examples in the computer, and it works every time. I'm like, OK, that's not a mathematical proof. So it took a little longer to prove it mathematically. But anyhow. So let's just try this, okay? I won't go through the proof of it, but just this is kind of like a fun little thing we can do, and a skill that you can have for the rest of your life, okay? So we just go through these three steps, okay? So the first step was to multiply the fecundities by R naught to the minus 1, okay? Which is what we have here, okay? And then the next step was to apply these Mason's rules. Okay, so we want to apply a rule here, and so which rule are we applying on this right here? Yeah, the first one, right? Yeah, because we're taking out that self loop and we're just putting in 1 minus A 1 1. Okay, so we want to now apply. Go from what we had in the previous slide and remove the second node. And so we can replace, if we go from node 3 to node 2 back to node 3, that's the self loop that has weight A32, A23, R naught to the minus 1. And then we just have these two self loops that are in parallel. And then we add this here, okay? And then if we have a loop that goes A21, A32, we then have a loop from 1 to 3 with that weight, and we have two parallels that we then add here, okay? So we now have this reduced graph with the middle node removed and a weight that goes A21, A32 added to this, and a weight A32, A23 R naught to the minus 1 to that. And then we have one last step where we multiply this one by this one and turn that into a self loop. And That's what we do here. And then we have these two in parallel, so we add them together. And get rid of that node. And then set the value to 1. And that's the number we get there. So this works in general. So if you prefer just to doodle on the back of an envelope, and you just remember those 3 rules, you can apply them, and it doesn't matter which order you apply them in. And the basis of the proof is that we can talk about the characteristic polynomial for a graph or for a matrix, and these rules somehow leave the characteristic polynomial invariant. Okay. And so, and I think when we do the lab, I'll throw a little example in there that you can just try for fun and see how it goes. Okay, so if we look at the net reproductive rate, yeah, absolutely, yeah.
Is there any biological interpretation of this procedure?
Yeah, no, I don't think there is. Yeah, this is really good. Maybe, let's see here. That's a really good question. I have a biological interpretation for R naught, but you're not asking about that. You're asking about, let's go to the biological interpretation for R naught and then come back, and I think there'll be some insight on that question. Okay, so this was, first of all, when we applied it to our Scentless Chamomile, now I've broken it down into 3 colors. Okay, and so we can write what we call these fecundity loops. And if we start with a flower, okay, and we go back to a flower, that goes from flower to flower. Okay, that's the green one. If we start with a flower and go to rosette and go back to a flower, that's another loop there. We could start with a flower and let me see, A31. Let me see here. So we go A13, A21, A32. That we go from the flower, we go to 1, then we go to 2, and then we go back to 3. Okay, so that's a loop that goes from 3 back to 3. Or we could start with the flower and then go to 1, and that would be A13, and then we could go back to 3. That would be A31. So we interpret the entries in terms of these loops in the life cycle graph where we're multiplying the weights together. And if we look at this term here, we need to include this somehow. And actually, I think I can turn the light on here. Is that right? Okay. And this piece of chalk. So we have a term A31, A13 plus A13, A21, A32, divided by 1 minus A1. But I'm going to write that as 1 plus A11 plus A11 squared plus A11 cubed plus like that, okay? And so I've just written this out as because we know this number is less than 1, I've written that out as a series. Does anyone have a sense of how to interpret this here? Yeah, so suppose we're interested in just this component here, A31, so this is equal to A31, A13, plus A31, A13, A11, plus A31, A13, A11 squared, okay, and then there'd be plus A13, A21, A32, plus A13, A21, A32, A11, plus A13, A21, A32, A11 squared. And it would keep going like that, okay? So if we thought about going from here and around here and then there, that would be a fecundity loop going back. Or we could go from here around and go back, okay? So we're seeing each of those, okay? This is without going around once. This is going around once. This is going around twice, and all the way on, okay? So even though our graph reduction rules give us the 1 minus A11 on the bottom, if we're going to interpret it biologically in terms of these loops, we want to write it out as an infinite series, okay? So that's the way I understand that, okay? Yeah. And so, yeah.
Is there any significance in the fact that they appear to be in relatively similar proportion? In 2004, it's like 20 times 2005.
Yeah, that's very interesting. Yeah, I think I think exactly the reason for that is because the change in the weather changed the flower production, and so the flower production affected the entire column of fecundities the same way. Yeah, so I think the fecundities are A13 and A32, oh no, sorry, A13, A23, A23, and A33. So A33, A23, A13, A13, and all of those have been increased or decreased by like a scaling factor that was to do with the flower productivity. So yeah, I think that's a very interesting insight, and I had never seen that before. So yeah, thank you. Yeah. So this is something that I think we can use for invasive species, and we have started to do this. There's a classical analysis that would use the eigenvalues, and in the computer lab there's some nice code I can show you to do that in a very painless and easy manner. But we can also do this kind of analysis, and we can do it analytically. And then from the analysis, we actually gain insight into what's driving R naught here for any particular weed. And so then if Dave wanted to use this for Scentless Chamomile in locally, right, there'd still be these coefficients, but he would have different values that he could then just plug straight in. Okay, so originally it was Alberta Research Council that wanted us to try to understand this. And they had these two possible biocontrol agents, and they said, we'd like to control this weed. It's an economic pest. There's a seed weevil that will reduce the production of seeds, and then there's a gall midge that reduces the vegetation. And so we can see how each of these control agents would affect the different terms in R naught, and immediately see how things would change intuitively. So in the lab, I've got a little bit of code to try to figure out how effective these things would need to be to actually control the weed. Okay, so I won't talk about that, but I will say that the most effective control agent was this species here, grad math bio studenticus, who was my student, who did mechanical control, removing the weeds, seed heads. And so he used this to simulate the control agents and validate the model. Okay, so turns out mechanical removal is actually the most effective thing here, more effective than these here. Yeah?
Have you compared this result with the result from the eigenvalue analysis that said that only 8 was?
Oh yeah, this is a great question. So I don't know if I included it, but No, I didn't. You can do sensitivity analysis for R naught as well. We did that, but I forgot to include it here. And the results are very similar. That it is the control of the fecundity that is the most crucial, A33, flower-to-flower transitions. And just like we took the elasticities there, we can do the same thing here. Yeah, that's a great question. Any other questions? Okay. Yeah, so we can apply this to all kinds of different invasive species. And it's not too hard to write down the life cycle graph, and we can often compute the R naught explicitly. And, but the difficulty now comes in parameterizing the model. This is where the lion's share of the work is, because we need to understand the quantities that go into that matrix. So why would we use this in controlling invasive species? Typically, we can come up with an analytical formula, and we can look at the effect of life history traits. It's complementary to looking at the eigenvalue, and it allows for the evaluation of control strategies. There was something that happened here that struck me as surprising the first time I saw it. And that was really what happened when we calculated R naught. And if we look at the matrix formulation here, when we take f times I minus t to the minus 1, we get a singular matrix. Okay, this is wonderful. This is really what we want. So if we have a matrix whose rows are all multiples of each other, then that's got rank 1, and then the eigenvalue just becomes a trace. We write down the trace word, and then we're good to go. But had we done all this work and got this matrix that was very very difficult to analyze for eigenvalues, we might not have been further ahead. And so the reason this works, in some sense, and the reason it works for epidemiological models, why you can write down R naught for an epidemiological model, usually explicitly, or for this kind of model explicitly, whereas your eigenvalue analysis requires the analysis of a higher dimensional polynomial, is something to do with the rank of f. Okay, so f is rank efficient, and then the properties of f times I minus t to the minus 1 are inherited from f. And we can interpret this somehow as saying it's only the third column that is producing new individuals. So all of the individuals have to go through the flowering stage. And so there's like a, what do you call that? Like a narrowing, or everything has to feed through that seed stage, right? Before it becomes something else. And this is what, there's a single stage it goes through. And so that's why this is explicit, because this is rank 1. So there's a theorem about that, but I don't want to go into the details here. The idea is that this is often a lot easier, though. And so, yeah, thanks for letting me share this with you. I can put these on the web, but there's a few references and so forth at the end, if you're interested. Thanks. Oh, thank you.
Would it work if somehow the system is not autonomous, like you did in this?
Ah, right. So are you thinking about like a forcing term, or that the A's could depend on time or something?
Some of the parameters, yeah. One of the AIJs is function of time.
Ah, yeah. Yeah. I don't know. I think that's a really hard problem. I mean, I know there is some theory of R naught for periodic A's, right? And I think some of the theory from ODEs could be maybe translated here. I think if so, the other direction is if your entries to your matrix are random variables, and so the AIJs come from some family of distributions. then there is some theory for stochastic matrix models. And so then your growth rate has a mean and a variance, and Shripad Taljaperkar has developed models for that. And of course, those kinds of models are quite apropos for these kinds of agricultural pest species. Yeah.
You said something about model validation.
Yeah.
What did that actually involve?
Okay, so I'm glad you asked. Yeah. So Thomas had a couple of years of data used to parameterize, and then each year he also did some mechanical control by pretending he was the biocontrol agent and either removing seed heads or destroying stems. And in these plots, he then would measure the new numbers in each of the stages from year to year.
And he was comparing it with the control.
He was
in the other sense, in the experimental sense.
Yeah, we had, you're right, we had the experimental control, and then we had the experiment, and then we had Thomas doing these biocontrol experiments without insects, that he was the biocontrol, and then seeing the effect on the parameters.
The parameters that were established that way in another year to predict how well would that work?
So I think there's a couple of issues here. So I think the overwhelming issue that I have mentioned but not addressed is that there's a great deal of year-to-year variability in the dynamics of the flowers, primarily due to the variable fecundity that depends on temperature and rainfall. So I think this is a rather crude measure, and I would estimate that in the long term it'll give an idea of what will work, but it's not going to be hitting the predictions head on. Yeah, good question.
Okay, so we'll send the speaker again.